Let's see an example. Here we have an example, it says refrigerator. So again, this is refrigerator. So this word means our objective is QL. This refrigerator uses refrigerant 134A. This is the name of the substance we are using as a refrigerant. And this cycle operates on ideal vapor compression refrigeration cycle between 0.14 and 0.8 megapascal. So 0.14 megapascal, this will be the high pressure we have here. 0.8, this will be the low pressure we have in our cycle. If the mass flow rate is 0.05 kilogram per second, find the rate of heat removal from the refrigerated space, find QL, find power input, find work input, find the rate of heat rejection, find coefficient of performance. Okay, so the first step, we have the TS diagram. So we know the pressures we have. So this will be the first pressure, 0.8 megapascal. So this pass 2-3 operates at 0.8 megapascal. This pass 4-1, this represents 0.14 megapascal. So again, we need to find coefficient of performance for this one. So coefficient of performance, this is the refrigerant cycle. So this one will be QL over work in. And what is QL? So if you see the example, so QL is H1 minus H4, inlet work H2 minus H1. So this one here will be H1 enthalpy at 0.1 minus enthalpy at 0.4 over enthalpy at 0.2 minus enthalpy at 0.1. So this will be the coefficient of performance. Okay. So now if we start with the points, so we can start with point number 1, state 1. State 1, this is saturated vapor at 0.14 megapascal. So this substance is saturated. We know the pressure. So you can go to the appendix for this refrigerant. By the way, this refrigerant is not water. So there are other tables for this one or figures. But anyway, I will make sure that you have it through the appendix. But just for state 1, then we can go to the appendix. And we can say enthalpy at 0.1. So this will be 239.19 kilojoule per kilogram. And also, since you are at 0.1, find entropy at 0.1. Why? Because 1 and 2, this is isentropic path. So whatever entropy you can find at 1, this will help you for your calculations at 0.2. So entropy at 0.1, this will be 0.94467 kilojoule per kilogram Kelvin. Now we can go to 0.2. This is superheated. And I know that its pressure is 0.8 megapascal. But one information is not enough for superheated or compressed phases. So we need another information, which is the entropy at 0.2. This is the same as entropy at 0.1, which is 0.94467 kilojoule per kilogram Kelvin. So now we have these two information. So we can go to from appendix. Then we can find H2, which is 275.4 kilojoule per kilogram. Then we can go to state 3. State 3 is saturated liquid at 0.8 megapascal. Then again from appendix you can find H3, which will be 95.48 kilojoule per kilogram. Then at state 4, state 4 is mixture of liquid and vapor at 0.14 megapascal. But we know that enthalpy at point number 4 is equivalent to enthalpy at point number 3 because this path is throttling at constant enthalpy. So this one is 5.48 kilojoule per kilogram. So now we have almost everything. So you can substitute in this equation. So we can say okay, so let's see, if I need to find the QL, in this example, he need to find rate of heat rejection. So QL, this one will be the mass flow rate given times H1 minus H4. So this is H1 minus H4. So this one will be the mass flow rate given 0.05 times H1, which is 239.19 minus 95.48. Then the amount or the rate of heat released, this will be 7.19 kilojoule per second, which is 7.19 kilowatt. And this is the first requirement we have in this example. Then we have rates of inlet work. So rate means we will multiply the specific enthalpy difference with mass flow rate. So this will be mass flow rate, which is given times H2 minus H1. So we have all the values in this example. So we can say this one will be 1.81 kilowatt. And this is the second requirement. Then from first law of thermodynamics, we know that QH is equivalent to QL plus work in. So if you substitute here, then the amount of heat at the higher temperature part of the cycle, this will be 9 kilowatt. And this is the third requirement. And last thing that you can substitute in coefficient of performance equation, then you can say the coefficient of performance of this refrigeration cycle, this one will be 3.97. And this is the last requirement you have. Is it clear? If I ask you, okay, if this cycle operates instead of as a refrigerant, I operate it as a heat pump. So what will be the coefficient of performance? So if remember, we said the coefficient of performance of heat pump is coefficient of performance of refrigerant plus 1. So this number, 3.97 plus 1, it will be 4.97. So this will be coefficient of performance of the same cycle if we are using this cycle as a heat pump instead of a refrigerator. Clear?